Hello everyone, welcome to this lecture in special relativity. Today we're going to discuss perhaps the most fundamental aspect of special relativity. It is really the reason why it was first discovered by Albert Einstein, and that is the connection between special relativity and electromagnetism. Okay, so let's start off by reviewing what we know about electromagnetism. So first of all, we know one fundamental thing about charge, and that is that it is not only is it globally conserved, it is also locally conserved. Okay? In electromagnetism, we have two fundamental sources that create electric and magnetic fields. One of them, denoted by rho, is the charge density. And this is a scalar quantity. And then the other is a vector quantity. It is a vector field known as the current density. And we all know that these can give rise to electric and magnetic fields. We also know that because of the local conservation of charge, these two densities, the charge density and the current density, must satisfy the continuity equation. Okay, so the local conservation of charge implies, or better, is equivalent to saying that this relation known as the continuity equation is true. Okay, this is also quite used in fluid dynamics. In a way, it's sort of saying that the charge and the current could be viewed as sort of a fluid that is that has conservation of mass. In fluid, you have conservation of mass, and here we have conservation of charge. Okay, great. Now, let's see if we can reframe this in the context of special relativity. We know that in special relativity, we have one particular form factor that is useful when expressing derivatives, and that is the Four gradient, right? The Four gradient, I'll do this in blue. The Four gradient is a four vector, which we often write as a square, and its components, right? I'll write the contravariant components. These are defined as derivative with respect to the four position, but with its covariant components, okay? So the contravariant components of the Four gradient are found by taking derivatives with respect to the covariant components of the position 4 vector. And so I'll write this out as 1 over c d dt, and then minus the typical gradient in spatial dimensions. Now, by similar logic, we can also write the covariant components of the Four gradient, and the zeroth component remains the same, of course, while the spatial components have a change in sign. Okay, wonderful. Now, why is this useful? Well, this is useful because you can clearly see that the continuity equation using the Four gradient can be written as this, where J mu, right, supposedly that's equal to rho times C, and then the current density. Okay, so it seems like the continuity equation, right? I'll label this as 1. We're going to have a lot of sort of important equations, right? 1 in relativistic terms becomes this. Okay, but we've also got to make sure that J mu here is a 4 vector, right? We don't know this yet. The reason we can write this is because we're conjecturing that this quantity right here, which I've written, is an actual 4 vector. Okay, so let's do this. One very easy way to see why is, well, look at this. So on the right hand side, I've got 0. This is a Lorentz scalar. On the left hand side, I've got a 4 vector contracted with something that I don't really know about. But that something that I don't really know about has to be another 4 vector, right? Because there's no other way I can contract a 4 vector with something and get a Lorentz scalar. So by default, we know from this that J mu right here is a 4 vector, which we call the 4 current. But I want to give you a more physical justification of why J mu is a current is a 4 vector. So we do our typical trick of considering different frames. Let me go down a bit. So let's consider 2 different frames. One frame I call S, right? So here I have a frame S. Actually, let me change color. So I've got a frame S, right? And inside this frame S, I have a finite region with charge density rho. Okay, so I have a finite region with charge density rho. So I'll draw this sort of as a bubble right here. And the thing about this is I can consider an infinitesimal element of this charge density, right? So I can consider a small infinitesimal cube of charge, right? And this will have infinitesimal volume, dr. Okay, now let's say that this frame S is moving to the right. First of all, let's assume that this block of charge is moving to the right with speed v relative to S. So I've got a block of charge with density rho, and it's moving to the right with speed v relative to S. Now, I also have, as I said, another frame which I will call S prime. And relative to S prime, S is moving with, say, a velocity u, right? And these don't necessarily have to be collinear, so they can be in different directions. Okay, so now, one crucial aspect to remember is that the total charge contained within this box has to be the same for both S and S prime. So these two observers must agree on what charge there is inside this box. The size of the box could change, the charge density could change, the velocity could change, but the total charge within that box has to be the same for both observers. Mathematically, we can write this as the following. So we must have that, rho prime dr prime, right, is equal to rho dr, okay? Now let's say that this block has a velocity, I don't know how to draw it actually, I'll draw it like this. Velocity w relative to S prime. Okay, the velocity of this is not just v plus u, because that's not how velocities add, unfortunately, in special relativity. but let's just say that it's just some W. In that case, there's a very famous relation which I've derived previously, which says that the gamma factor of this speed W is equal to gamma V gamma U times 1 plus U dot V over C squared. Now this is quite useful. Why? Because first of all, we know that dr prime, right, because of the Lorentz contraction, would be equal to what? To dr of 0. What is dr 0? dr 0 is the let's use a different color. I'll use yellow. dr 0 is the rest volume of this box right here. Okay, so this box in its own frame has volume dr 0. So because of Lorentz contraction in the frame S prime, it will have volume dr 0 divided by the gamma factor of W, because that's the speed of this charge relative to S prime. Okay, but now we can use the identity that I wrote above, right? This can go into here, and I can write this as dr 0 divided by omega V omega U 1 plus U dot V over C squared. Okay, but now we also have to note that in frame S, dr is going to be equal to dr 0 divided by, now this time it's divided by the gamma factor of the velocity of the speed of the charge relative to S. And the speed of the charge relative to S is V. Okay, so I should have done this in red. So dr is equal to dr 0 divided by gamma V. But I've got that right here. So I can write this as dr divided by gamma U 1 plus U dot VO divided by C squared. So this gives me a relation between the volume of this box relative to S prime and S, okay? Wonderful. This I can use. Why? Because I've also got this important relation of charge conservation. So if I plug it in here, right, what do I find? Well, I find that, okay, so plug this into, I'll call this 2, right? So plugging into 2, what do we get? So rho prime is equal to dr over dr prime times just normal rho. Okay, so this is equal to, well, we've got dr over dr prime from here, right? That's just equal to rho u 1 plus U dot V over C squared times rho. Sorry, rho should be red. Fine. Now we also use the fact, there's another fundamental relation between the charge density and the current density. right? And that is that J, the current density for a given charge density that is moving, is equal to that charge density times the velocity at which it is moving. Okay, so that's an important relation from classical electromagnetism that you should remember. And when I plug that into here, I clearly see, well, here, rho times v, right? Well, that's just equal to J, right? So this is equal to rho u times gamma u times rho plus u over c squared dot J. Okay, let me write this in white because we've got our fundamental relation. So we have the transformation of charge densities. We have derived it, and it reads rho prime equals gamma u rho plus u over c squared dot, u dot J over c squared. Okay. This is how the zeroth component of a 4-vector changes, right? The zeroth component of a 4-vector, A0 prime, is equal to gamma u A0 plus u dot A, where this is the spatial part of the 4-vector, over c squared. Over c. Now, the reason I don't have that problem here is because it turns out that the actual zeroth component of our 4-vector is not rho, it's rho times c. So if I write it as such, I get rho c plus u dot J over c, which is indeed equivalent to this. So this is our relation, which is really hinting at the fact that the 4 current I've defined really is a 4-vector. The calculation for J is pretty much the same. I'll do it quickly for completeness. So what do we have? Okay, so let's do the transformation of the parallel component, right? So this is equal to rho prime, right? That's the charge in the prime frame, times the velocity of the charge, which is omega, parallel to the velocity we're transforming along. Okay, we found this. We found rho prime. It's just gamma u times rho plus u dot J over c squared multiplied by this right here. Okay, now a little trick here is to rewrite J in its original form. So this is equal to rho W parallel plus u dot V over c squared rho W parallel. Now we use the fact that W parallel from the velocity addition is equal to u plus v divided by 1 plus u dot v over c squared. This is another one of those important special relativity relations. And this just gives you, after some simple algebra, gamma u rho u plus v. We're almost there. Actually, we're pretty much there. Why? Because this tells me that this is equal to gamma u j, right? This j is this rho times v. That's where I get my J. Plus rho U. And, well, lo and behold, this gives me another Lorentz transformation if I rewrite it in the following way. If I write it as J parallel prime equals omega U J plus U over C rho C. So there you go. This, that's a bit long. And this is, again, entirely analogous to how the spatial components parallel to the transformation velocity transform in special relativity as such. Okay. So we see this correspondence. Now, there's the derivation for the perpendicular component is very similar. I'll leave it to you, but you will easily find out that this happens. Just use the velocity addition rule that W perpendicular is equal to V over omega U 1 plus U dot V over C squared. If you use that, you will find the correct result. C squared. Okay, so we found that the current density is indeed a 4-vector. Okay, so this is our first important result. 1 J mu equals rho C J is 4-vector. And it satisfies the continuity equation. So that's our first very important result right here. Okay. That's one aspect. Now here is the second important point to remember, and that is gauges. Now, if you don't know what a gauge or what a gauge invariance is, it's a specific aspect of Maxwell's equations. Essentially, there are different mathematical expressions for the potentials related to a vector field that can give the same result back and that can have the same physical interpretations. More precisely, if you look at what Maxwell's equations read, right? Maxwell's equations are the following in free space, so I don't have to worry about materials and polarizations and stuff. They look like this. Okay. That's Faraday, and finally Ampere Maxwell. Oops. Okay, so these are Maxwell's equations in all their beauty. We will make a lot of use of them. One important thing that you should remember from your electromagnetism course is that we can define a vector potential, which we call A, which we write as A, such that B is equal to the curl of A, right? And this is because of, firstly, the Helmholtz theorem. The Helmholtz theorem tells you that you can write any vector field as a sum of a gradient and a curl. Okay, but why don't we have the gradient here? Well, because we need this to happen. We need the magnetic field to be divergenceless, and so this tells us that we can always find the vector potential as such that its curl is equal to B. Indeed, if you take the divergence of the curl, you always get 0. Okay, so this is how we define the vector potential. What consequences are there on how we can define on the electric field, right? And you can see the consequences of this definition by using just Faraday's law. So if you look at Faraday's law, I get curl of E is equal to minus derivative with respect to time of the curl of A. And if I move everything on one side, I get that the curl of E plus dA dt, I get 0. Okay, so I found that the curl of a vector field is 0, but that, by the same reasoning as here, tells me that I can always write E plus dA dt as the gradient of a scalar field, phi, where phi is often referred to as the scalar potential. Okay. In other words, E is written as for historical reasons, we usually just put a minus here. So minus grad phi minus dA dt. Okay, so essentially we can rewrite Maxwell's equations instead of using E and B by using A and phi. Okay. Now, one might think, okay, so if I give you a certain electric and magnetic field, are A and phi well defined? Is there only one set of A and phi that will give me E and B? Well, the answer is, of course not, because of gauge transformations. Gauge transformations are transformations that you can apply on phi and A, which will still give you the same E and B. Okay? How can we see what these gauge transformations are? The easiest way is to look at at the second gauge identity, this one. So how can I transform A in such a way that when I take its curl, I get the same thing back? Well, simple. I can add the gradient of a function to A, and because the curl of a gradient is 0, I will always get the same B back. In other words, if I apply this transformation, I add the grad of chi, or C, I don't know how people pronounce it, I'll pronounce it chi. The grad of chi, if I add it to A, will still give me the same B, right? So this tells me that B transforms to the curl of A plus grad chi, but the curl of the grad is 0, so we just end up with the curl of A, which is of course B. Okay, similarly, similarly we can find a similar gauge transformation for E, but we've got to be a bit more careful about E. Okay, so how does E transform? Well, E transforms to minus grad of phi minus dA dt minus d grad chi dt. Okay, this is a bit of a problem because I'm not getting the same E back. However, I can make sure that I do get the same E back if I also transform phi. If I transform phi as phi. So if I do a minus, right, then it will be minus grad psi plus derivative with respect to time of grad chi. And so then these two cancel out. Okay, and that's how I get my E back. Okay? So you can check it for yourself. These two transformations give me the same E and B. But now here again, the 4 gradient comes to our rescue. This is because I can write these transformations in the following way if I get very clever. Let's say I define this new candidate 4 vector. I still don't know if it is, but I can still write it, say, okay, these are the components of some quantity. And this quantity has components phi and phi over c and a. Okay? Now, if I define this, then these gauge transformations take on the following very simple form. A mu gets mapped to A mu minus derivative mu chi. No, sorry. Derivative mu chi. Why? Well, let's expand this. So this is equal to, so the first component is just phi over c. So this is telling me phi over c gets mapped to phi over c minus 1 over c d chi dt. And if you multiply by c, you get the transformation of the scalar potential. And similarly, so this is the 0th component, and the 1, 2, and 3 spatial components instead tell me that A maps to A plus gradient of chi, which is exactly the gauge transformation for the vector potential. So this is how I can write my gauge transformation in using 4 vectors. And this is again hinting at the fact that this quantity right here should be a 4 vector. How can we test this though? How do we know for sure? We have to develop something called a Lorentz gauge. Okay? A gauge essentially is just choosing a specific type of A and phi, given that there's this redundancy, this gauge invariance, where I can choose an infinite type of A and phi. Choosing one family of these potentials is what's known as setting a gauge. Now, one gauge that is often used, especially in classical physics, is something known as a Coulomb gauge. In the Coulomb gauge just says, okay, I want my vector potential to be 0, to be divergenceless, right? And if you choose this, then what you can essentially rewrite Faraday's law as the following. So this is just the curl of B, right? This is B is equal to mu j plus 1 over c squared derivative with respect to time of E, which is minus grad of psi minus minus dA dt, right? Next, this is equal to the gradient of the curl of A minus the vector Laplacian of A. And what is this equal to? This is equal to mu 0 j minus 1 over c squared derivative of grad phi with respect to time minus 1 over c squared derivative with respect to time squared. Okay, this is 0 because of the Coulomb gauge, right? That I just said. Coulomb gauge. We find that Laplacian of A plus 1 over c squared, minus 1 over c squared times this is equal to 1 over c squared times the derivative of the gradient of phi with respect to time minus mu 0 j. As you can see, this is not a very pretty equation. There are ways to simplify this by assuming that j can be decomposed into transversal and longitudinal components, but it's very hard to go into a simpler form. The reason this is also not a very nice choice if you're dealing with relativistic effects is that it doesn't treat space and time on equal footing. I can't really write this in a Lorentz covariant way. It just doesn't look nice. Okay, our goal is to be able to find a way to write this in a Lorentz covariant way. And I'll do this as follows. So I'll start off again with this equation, but I won't assume the Coulomb gauge, right? So I get this is equal to mu 0 j minus 1 over c squared there we go. So my question is, can I find a more suitable gauge? One way is to notice that I can write, I can bring this on this side and include it into this gradient, right? So I'd have gradient of divergence of A plus 1 over c squared derivative of the gradient of phi with respect to time. If I could set this equal to 0, it would simplify a lot. Or better, in reality, it's probably easier if I set the thing inside this gradient to be equal to 0. So I will set what is inside this gradient to be equal to 0, right? This is known as the Lorentz gauge. Now, there are uniqueness theorems that tell you that you can always find a solution to the Lorentz gauge, essentially because it boils down to solving a Poisson equation which has uniqueness theorems. So if I can set this equal to 0, then this vanishes because it goes in with this, right? And so what I'm left with is 1 over c squared derivative of a, second derivative of a with respect to time, minus Laplacian of a is equal to mu j. Wonderful. Now you can do a similar calculation by you can do a similar calculation for the scalar potential, right? By using Gauss's law, and Gauss's law will tell you what it will give you. So now we're using Gauss's law. The divergence of the gradient of phi minus grad phi minus derivative of a with respect to time is equal to rho over E0. Okay, so this is equal to minus the grad square of phi, or better, the minus Laplacian of phi. Now I can use the Lorentz gauge, right? To replace, I would get the derivative with respect to time of the divergence of A, but the divergence of A is minus 1 over c squared times this derivative. So minus 1 over c squared times the derivative that's right. Here I should not have a gradient there because it gets sucked into this gradient here. So it's just the derivative of phi with respect to time. Okay? And so I got that 1 over c squared. Now what I'll do here is, I'll do it later actually. So derivative with respect to time squared of phi minus Laplacian of phi is equal to rho over E0. But remember, in our original definition of our candidate 4-vector potential, I used phi over c. So I want to write this as phi over c, just to see if I can write this in a nice way. So phi over c, I'm dividing everything by c, so I should also divide here by c. And that will give me mu 0, rho c, right? Yeah, that's right. Okay. So this is our second wave equation, right? This is our wave equation for the vector potential. This is our wave equation for the scalar potential. And we can write them in a very nice way using relativity, using the so-called D'Alembert operator. The D'Alembert operator is just the contraction of the 4 gradient with itself. So it's easy to see that it takes the following form. Because it's a contraction of 2 Lorentz 4 vectors, it is as Lorentz scalar. Okay, so I can immediately recognize that these equations can be summed up into just one neat equation, which is right? Very cool. So these two wave equations have become one wave equation. I haven't lost any information. I will still get these equations out of it. I've just written it very neatly. Also note that the Lorentz gauge can be written in another relativistic covariant form. Indeed, this is just, I can write this as phi over c and get 1 over c here. And so this just gives me that for gradient contracted with the vector potential is equal to 0. Okay, so this is the Coulomb gauge written in manifestly covariant form. The Lorentz gauge written in manifestly covariant form. Okay, so there you go. So we have used our gauges and we have essentially mathematically proven that A mu is indeed a 4-vector. Why? I've got a Lorentz scalar here, I've got a Lorentz scalar here, I've got a 4-vector here. So this has to be a 4-vector, right? Because say I do a change of transformation, this won't change, this won't change, this won't change, but this will definitely change if it's not a 4-vector. You could do the same here, right? Although this is more of a condition that is set upon rather than a physical equation. Okay, so very good. We have proven, therefore, A mu is a 4-vector, satisfying. If it satisfies the Lorentz gauge, then it will satisfy this wave equation. So very good. This is the end of our part 1 on connecting special relativity with electromagnetism. In the following part, we'll see why we can use the wave equation, the Lorentz gauge in general, to recast Maxwell's equations in a manifestly covariant form.